Hello. Today we're going to go over some electromotive force and what that is. But before we do that, let's just take a little recap of Lenz's law. Remember, Lenz's law is that there will be a current that becomes induced in a conductor, which will produce a magnetic field that opposes the change in whatever current magnetic field there exists. So we first have to ask ourselves, what is the change in the current field that is existing? Then we ask ourselves, what will oppose this type of change? And then we can use our right-hand rule to determine which direction this current will have to go to create this induced field. And the way that we can quantify the amount of induced field is through this concept of flux, where the flux is the magnetic field strength multiplied by the area exposed to that field. The electromotive force is where we go from here, where the electromotive force in a loop, which we signify with this curly E, is equal to N being the number of loops. So in a singular loop, N would be 1, but solenoids are often made of multiple loops, so each loop would see the same change in flux, multiplied by the change in flux per unit time. EMF, ooh, that's messy. EMF is voltage. That's the units of EMF, which means EMF is the joules per unit charge moving, or EMF is potential, electric potential. And this relates because sometimes we're going to see that we're dealing with circuits, so you might have to remember Ohm's resistance law, where the voltage is also a relation of the current and the resistance. For example, this there's a square loop. It's a singular loop, as we can see, has a size of 0.25 meters and 12 ohms of resistance. Is placed perpendicular to a 1.5 Tesla magnetic field that is directed upward. The magnetic field reduces strength to 0.25 Tesla in 5 seconds. What is the current in the loop, and which direction will it go? Well, if I have a field that is pointed upward, so kind of like there and there and there. Here we go. I have a field directed upward, and I put a loop that is perpendicular to it. So kind of something like that. So it's level with the ground. Remember, the only thing we're paying attention to is the field that exists on the inside of the loop. I'd first, step one, check my Lenz's law. Lenz's law is saying that this field is reducing in strength. And so step one, the field is reducing in strength. Step two, I ask myself, okay, if the field is reducing in strength, then what's going to happen is I'm going to have to, if it's reducing in strength, I'm going to have to produce a field to oppose that change. In other words, I'm going to induce a field upward to oppose that. And what sort of current will have to be to make a field upward? So if you take your right hand and you want to point your fingers pointing up, notice where your thumb goes. Any way that you rotate your thumb when your fingers are pointing up, if you are looking from a top-down perspective, in other words, your fingers are pointing up and you're looking at your fingers, you notice that your thumb will rotate in a way that is in a counterclockwise. So I would say, one, our direction is counterclockwise from a top view. So we know which direction that current is going. And to find the magnitude of the current, well, if I want to know my current, just a rearrangement of Ohm's law here, it's V over R. we are very well aware of our rate of our resistance. It's 12 ohms. This voltage is what we want to find, and the voltage is found by using the EMF. So the EMF is equal to the number of loops multiplied by the change in flux over the amount of time that takes. In this case, we have one loop. When I'm thinking of flux, remember field times area. Is my field changing or is my area changing? In this case, it's the field. So I'm going to be looking at my change in field. So I went from 0.25 Tesla at the end, from 1.5 Tesla at the very beginning. And the area is, it's a square, side length. So square is side length times side length. So 0.25 squared over 5 seconds. So 0.25 times 0.25 should be 0.0625. And 0.25 minus 1.5 would be 1.25. 1.25 divided by 5 would be 0.25, so 0.0625 times a quarter of that is, I'm guessing 0.1. Oh, hell. I'm going to just bring in my calculator. That would be a good idea. I get an answer of 0.015625. 0.015625. And to find our current, we would then divide that by 12. I just closed my calculator and I don't feel like opening it again, but you can just shove that in. That's fine. Feel free to double check. I might have punched something wrong into my calculator again. Don't pay attention to what I am very poorly drawing with my mouse here. Pay attention to what you can do. It's all about relating your change in flux as a function of time. Now, there are some tricky ways for us to change the flux. This one is very straightforward. We change the strength of the magnetic field. The magnetic field got weaker. But we can change the flux by moving things. So remember, we're always looking for a loop. It used to, the conducting bar on these two rods that allow conduction through it, started in this started out space, and there's a particular amount of flux. But when it moved, we noticed that the flux is increasing. There's a larger flux. If there's a larger flux, that means there's a change in flux, and a change in flux is going to create a induced current. So we look at this one, we say, okay, what's happening? The field is pointed into the page. When the bar moves, the flux increases. If the flux increases, then the opposite is going to be working against the flux. It looks like my induced current has to be out of the page. Sorry, my induced field has to be out of my page. And you pick up your right hand and you use your right hand rule. It looks like the current that we're doing here is going to be a counterclockwise current. And then we would be able to use, so that's us using the right hand rule and Lenz's law to determine the direction of our induced current. The next thing is, how am I going to find my EMF? Well, your EMF is N, just 1, multiplied by your field. Notice it's not the field changing, so it'll be multiplied by the change in area over the time. Now, this one, you might notice that we have length. Area is going to be just length times width, but the width is here denoted as x. So it's length times x. In this case, since x is changing, well, we can actually have L times the change in x, because that's the thing that's actually changing. B is constant, L is constant, but delta x is the one that's changing. That's divided by t. And you might notice, hey, what do we have going on here? My change in x over time, that is the velocity, because that velocity is my x. So the EMF for a moving bar like this actually simplifies to BLV, because L times V is your change, is your rate of change, rate of change of this magnetic field times that length, multiplying by that turns it into an area, so it is a flux. So magnetic field multiplied by change in area, rate of change of area, is another way of doing it. So this is one tricky way of doing it. Another, if you move a loop in and out of a magnetic field, you'll notice that this is the exact same situation as this, just instead of having a fixed set of rods and moving a bar, here I'm moving the rods with it. But we still have just an area of flux that, as this loop goes in, becomes larger and larger. The field is maybe bounded by something, but as the loop goes in, there's a certain flux. So this follows the exact same behaviors. A spinning loop is the alternate way to do this. Now, or when a loop is magnetic, when a loop is parallel to the magnetic field, remember this is like when I put that piece of paper in front of my face, when it was parallel to the direction you're looking, you were not really able to see much of the paper. You're looking on it on edge. So when the loop is parallel to the magnetic field, the flux is zero, because there's no visual acuity. You can't, because there's no field lines that are actually passing through. And when the loop is perpendicular, the flux is full, whatever its quantity is, it's at its absolute fullness. So if you consider a loop, if you consider a piece of paper, if you spun it 360 degrees, you get back to the exact same place. And that's not looking like a change. And if you did half of that, if you spun it 180 degrees, if you did half spin, it's still back to where it was in the first place, and that is no change. So where you're seeing the change isn't a full turn, and you're not seeing the change in a half turn. You're actually seeing a change. And again, if you're not sure, pick up a piece of paper, hold it out in front of you. You see the greatest amount of change when you only turn it 1/4. So it's a 1/4 turn is what we're dealing with here. And frequency is defined as the number of cycles or number of turns that occur within 1 second. So for us to do this, the idea for finding our EMFs, remember our EMFs is the change in flux, which is easy. You're just going to take the field times the area. When it is at, it's just field times area at full, and it's just 0 so it's full, or B times A at perpendicular, and it's 0 when it's parallel. And you want to divide by the time for a 1/4 turn. And that would be the rate of change of flux, because it goes from full to 0 in a 1/4 turn. So if you know the frequency, it's how many turns per second, you can find the time for a 1/4 turn. Let's take a look at this. 120 hertz. 120 hertz is 120 turns per second. So 1 turn should take 1/120 seconds. So the 1/4 turn should be 1/4 multiplied by 120 seconds. So it's only 1/480th of a second. Using this, I can then take my circular loop, take my magnetic field multiplied by the area of a circle, remember, pi r squared. That would get me my change in flux from going from parallel to perpendicular, and I can divide it by 1/480th to determine the EMF induced in this particular circular loop. That's what EMF is. That's how we calculate it. Practice up and make sure to ask questions. Bye.